Hello, this is Lab 6, Magnetic Molasses. So the main purpose of this lab is to observe Faraday's law's interactions and how they affect the speed of a falling magnet through a conductive tube, and to model how these interactions between the magnetic and electric field work in a computational model. So our main formulas that we're using is the general magnetic dipole formula, the induced EMF formula, and the induced current formula, which is just derived from your induced EMF formula. And the EMF formula is based on Faraday's law. So our main findings was that the observed time for the magnet to fall through the tube was an average of 1.12 seconds, and the computational magnet found that the magnet took 1.091 seconds to fall through the simulated tube. So we use the magnetic general dipole field formula because this gives us the magnetic field due to a dipole at any location in space, which is used to find the magnetic field produced by the falling magnet at different points in the tube. Then the EMF formula, this formula gives us the EMF induced due to the magnetic field based on the change in flux through a surface, which is used to find the EMF in the rings that make up the tube that is induced by the falling magnet. Induced current formula is just to give the current in those rings, which helps you then find the magnetic force by those rings, the magnetic field from those rings. And that's just dividing EMF by R. Assumptions. So we're assuming that we have an ideal magnet, which is that the magnet being dropped is an ideal dipole and outputs a dipolar field exactly. Like it's not a quadrupole, it's not an octopole, it's specifically a dipole. And the tube can be approximated by concentric rings that are a small distance apart. Basically, that our tube is rings and not some other surface. These assumptions make it possible to create our computational model, which can help us approximate the time it should take. Experimental diagram. So we have the magnet that's falling through the tube. The system is the magnet and the tube, and the surroundings is the earth and everything else. Our initial conditions is that the magnet has no velocity. It's at the top of the tube. It has that mass, that dipole moment. The tube length is what is stated there. The inner radius and the thickness is what's stated. And basically in this tube, the magnet has two forces. It has the magnetic force from the tube onto the magnet going up, and gravity is pointed downward, and these forces oppose each other. Gravity is greater than the force magnet, which is why it continues to go downward. So our experiment details, so first we're measuring the dimensions of the tube, then we set up a stopwatch, drop the magnet 5 times, recording the time it took to fall through the tube each time, and taking that average. So our computational model, initial conditions are same as from the experiment, but additionally we set the U0 over 4 pi. We set mu mag once again. We set the resistivity of the aluminum. We're also given G, and then the thickness of the tube segments and delta T are specific to the creation of this model. And so magnet's dipole, tube is represented as a stack of rings that can carry a current. So then this is what these code snippets here set up our calculations that are done to find the forces on the magnet, and then I'll also calculate the magnet position and velocity at each discrete point in time as you go through the time by steps at delta t. So then our results, shows tube is a gray cylinder, magnet is a red object, and the left shows graph velocity over time. So the speed increases as you enter the tube, and then it levels off at a terminal state, and then increases again as the magnetic transitions to only being acted on by gravity. Similarities is that the time it took was pretty similar between our computational model and the actual experiment. Our differences is that the computational model is only an approximation and does not model it exactly. The model generates a tube as many stacked rings, while the real tube's continuous object. The model also only checks the time at discrete steps, which is really close, but in the real situation, time is continuous. The consequence of this is that the kinematics are also approximate, which does affect the overall outcome, but it's pretty close because also our measurement from mu mag from the previous lab isn't exact either. Error sources, measurement of tubes could be wrong, the time measurements could be wrong, our dipole moment that is input for the model could be wrong, our assumptions could fail, which means the magnet might not be an ideal dipole, or the tube approximation as rings could be turn out to be bad. So if the resistivity of the conductor was close as possible to 0, then the current in conductor would increase dramatically, since I is EMF over R, and if R approaches 0, then the current would go to infinity, which would mean that the magnetic force would also get really large. But this would happen for a short period of time because you need the flux to be changing. So when you get to 0, then the flux, when the magnet has a velocity of 0, the flux would stop changing, which would then, so it would just stop. The magnet would just stop in the tube. It wouldn't go anywhere, but it would just stop. If holes or slots are cut in the tube, the ring model would break down because you can't represent the tube as a stack of rings since the rings wouldn't be like complete in certain places. So in order to model that situation, you need to use a different open surface. And overall, our model was pretty close, around 1.1 seconds for both the magnet and the real situation. But it can't model it exactly, but it's pretty close. That's it.